Hi everyone, so in this video I want to introduce the notion of a continuous random variable and kind of discuss the difference between how to identify whether a random variable is continuous or discrete, and then talk about how we can look at probability distributions when we are dealing with a continuous random variable. So let's consider the following example. A manufacturer of lithium batteries sends out shipments and they weigh the weight of each box that they send out to the customers. So let's let X denote a random variable which corresponds to, which is going to map a randomly selected box of batteries to its corresponding weight. And so let's think about what some of the possible values for X, this random variable X, could be. So it's possible that this box of batteries weighs exactly 5 pounds, or maybe a randomly selected box weighs exactly 6 pounds, in which case it could be discrete. But when we're measuring weights of boxes, right, this could be any value actually between, say, 0 and infinity in this case. So you pick a randomly selected shipment, it's probably not going to weigh exactly 5 pounds or exactly 6 pounds, but if we could measure its weight more precisely, we would see that it's something like 5.3671 pounds. So one thing to notice here is that it is possible for a random variable to map to a value which is not an integer in the case where, for example, we're measuring weights. So I don't want to redefine what a random variable is to handle these situations like when we're measuring things, but let's just recall in general, a random variable is a mapping from a sample space of some statistical experiment into the real numbers. So for each outcome in the sample space, we map it to a number, a real number. So with a discrete random variable, this sample space is mapped not into the real numbers, but integers or a subset of the integers. So this would be, for example, when we're counting how many batteries in a shipment are defective. So those values can only be 0, 1, 2, 3, and so on. So when we're counting things, we're mapping to integers. These are called discrete random variables. On the other hand, when we're measuring things such as the weight of a box, this is something that could be any value, not just integers. So it could be some decimal value. So in that case, with a continuous random variable, the sample space is mapped into an interval of values in the real numbers. So a continuous spectrum of values in the real numbers. And so, for example, this would be when we're measuring things, typically we're not getting integers, but we're getting really precise measurements that could be that can range continuously over an interval from its minimum to its maximum value. So when we're counting things, we're thinking about discrete random variables. When we're typically measuring things, these are going to be continuous random variables. And so let's use this example of random variable X is going to map a randomly selected shipment of batteries to its corresponding weight. And so if we were to weigh each of these shipments to its nearest pound, then this would map each box to an integer. It weighs 0 pounds, 1 pound, 2 pound, and so on. So in graph A over here, what we are looking at is the weight of a shipment rounded to the nearest pound. So we actually are looking at a discrete random variable over here. And so if we wanted to answer, for example, what is the probability that a shipment of batteries weighs between 1 and 3 pounds, then what we would need to do is look at this distribution that we have in A and add up what's the probability that it weighs exactly 1 pound, what's the probability that that shipment weighed 2 pounds when we rounded its weight, plus the probability that the rounded weight of the shipment was 3 pounds. So we would add up the areas of these three rectangles, and that would give us an approximation for what is the probability that a random shipment of batteries weighs between 1 and 3 pounds. So this is what we've been looking at with discrete random variables. When we are measuring things, however, such as the weight, right, we can make this more accurate. So for example, I could choose to measure the shipment not to the nearest pound, but say to the nearest quarter pound, right? And then we would have more rectangles that are more narrow. And now if I wanted to calculate what is the probability that a shipment of batteries weighs between 1 and 3 pounds, we could do a similar thing as we did in graph A, which is we could sum up the areas of the rectangles from x equals 1 to x equals 3. Just now, we're going to have a lot more of those rectangles because we have measured things more accurately. So I might add up this rectangle, this rectangle, this rectangle. We're going to add up all of these rectangles between 1 and 3. So we would stop over here. So now we can think about the area of all of these rectangles would tell us an approximate probability that a randomly selected shipment would weigh between 1 and 3 pounds. And now if we take this out even further, let's say we could measure precisely each shipment, then what we would get is a continuous graph. So we would get a probability distribution which is no longer rectangles but is a curve. And if we want to still calculate, well, what is the probability that the shipment weighs between 1 and 3 pounds, we still are going to want to calculate an area. Just now that area is not going to be able to be calculated using rectangles. So I go to 1, I go to 3, and we would want to calculate this area right here. And so if you're looking at this picture, hopefully this brings to mind some notion of how we can use Riemann sums to come up with an approximation for a value of a definite integral. So with the discrete situation, we were adding areas of rectangles with a continuous distribution, continuous random variable. We're going to need to integrate in order to calculate the exact value of this area. So for example, this area that we have over here could be represented as the integral of the probability distribution over the interval from 1 to 3. And so now let's discuss what a probability distribution would look like for a continuous random variable and what properties this function should satisfy. So when we have a continuous random variable, the probability distribution is also called the probability density function, which is abbreviated with a PDF. So with discrete random variables, we called them probability mass functions, a PMF. With a continuous random variable, we oftentimes call these probability density functions, and we abbreviate it with PDF. But we're going to use the same notation. So this subscript x is referring to the fact that this is the probability distribution of random variable x. And here's a graph of what that function might look like. And so let's think about some properties that this probability distribution should satisfy. And it's going to be similar ones that we had for the discrete random variable. So the first thing is, since this is telling me something about how likely, what is the probability that the random variable x takes on certain values, the value of a probability distribution has to be greater than or equal to 0. So that's why this graph that we have on the right, is above the x-axis because f of x is always positive. Okay, next is that when we integrate over the entire sample space, so this is kind of representing what's the minimum value of x, which can't be less than minus infinity. And up here, we've got the maximum value of random variable x. So if we integrate from the minimum value of x to the maximum value of x, that would be saying what's the probability that random variable x is anywhere from its minimum to its maximum value. And again, that must equal 100%, since the probability of the entire sample space should be 100%. So the total area underneath this curve should be 1. And then lastly, why do we like having probability density functions? Well, we can use them to help us calculate probabilities. So if, for example, I wanted to calculate the probability that random variable x is greater than a but less than b, then what we would want to do, as we saw in the previous example, we would want to calculate the area underneath this curve over the interval from x equals a to x equals b. So that's this gray shaded area over here. So when we are going to calculate probability densities, when we're going to calculate probabilities for a continuous random variable using a probability density function, we're going to want to calculate areas underneath that curve, which might require us to use integrals. Okay, so to close things out for this video, let's consider the following example. So our sample space is going to be the set of all students at a university. So that's going to be omega. And the random variable x is going to be what we get when we randomly select a student, and x is going to map that student to their GPA. And so since we take a whole lot of classes, right, your GPA is not a discrete random variable. It's not just 0, 1, 2, 3, or 4, but it could be any value in between. So this random variable is going to map from the set of all students into the closed interval from 0 to 4. So the minimum value for this random variable is 0. The maximum value would be 4. And so down here, we've got a hypothetical graph for such a probability density function. So at this university, you can see that most students have a GPA of 2. And then as we move up from 2, it's less and less likely that students have higher and higher GPAs. And as we move down from 2, we get less and less likely that a student would have a really low GPA. So altogether, you can check that the total area underneath this curve should be 1. So calculating what's the probability that a student's GPA is between 0 and 4, this should give us 100% of the students at the university. And here, this area, right, would be a triangle. So we could say this triangle's area would be the base, which is 4, times the height, which is 1/2. So the area would be, the total area would be the 1/2 base, which is 4, times the height, which is also 1/2. And that gives us 1. Okay, so this total area is telling us, great, 100% of the students have a GPA between 0 and 4. So if in question 1, we want to go ahead and calculate what is the proportion of students at this university that have a GPA between 3 and 4. In other words, if we randomly selected a student, what's the probability that that student's GPA would be between 3 and 4? And so with continuous random variables, this would be the value of the integral of f of x over the interval from x equals 3 to x equals 4. So we certainly could integrate this if we had, we can find the formula for this function, but since this area happens to be a triangle, we could simply say it's going to equal the area of that triangle, which is 1/2 times the base. So the base has a width of 1, and over here we can see the height is 0.25 over here. So it's going to be 1/2 times 1 times 0.25, which gives us 0.125. So this tells us that about 12.5 or exactly 12.5% of the students at this university have a GPA between 3 and 4. In the next question, we want to calculate what proportion of students have a GPA between 2 and 3. And again, this would be the integral from 2 to 3 of the probability density function. So that would be this area in blue of this trapezoid over here. So again, we don't actually need to integrate because we could calculate this area of this trapezoid using more standard formulas from geometry. So one way that I could do this would be to take into account that this entire area of blue plus green, right, is equal to half of the total area underneath this curve. So between the blue and the green, these areas should add up to 1/2. And what we're going to subtract out in order to get the part that's just in blue is we can take this entire area of this entire triangle, which is where the 0.5 comes from, and then we're going to subtract out this piece in green. And we found in the first part that that green area is equal to 0.125. And so taking the entire area of the triangle, which is 1/2, subtracting the area in green, which is 0.125, this would tell us what the remaining area is, which is the blue area, and that comes out to 0.375. So this tells us, therefore, that about 37.5% of students at this university have a GPA between 2 and 3. So when we're going to calculate probabilities for continuous random variables, we're going to need to use some tools from calculus, namely integration techniques.